Let's work this example. A 20 kilogram cannonball is fired from a cannon with a muzzle speed of 1,000 meters per second at an angle of 37 degrees with the horizontal. A second ball is fired at an angle of 90 degrees. Use the isolated system model to find the maximum height reached by each ball and the total mechanical energy of the ball-earth system at the maximum height for each ball. Let y equal 0 at the cannon. Alright, so let's write what we are given here. Let me make my pen a little bit bigger. So we have a mass of 20 kilograms, initial velocity of 1,000 meters per second. The first angle we're considering is 37 degrees. Call that theta 1. The second angle, call that theta 2, is 90 degrees. So this will be case 1 and case 2. Alright, now first thing we need to consider is this is an isolated system, meaning there's no energy transfer across the system boundary. Or, as an equation, you could say that the change in energy of the system is equal to 0, or it's conserved. Let's think about the system. It's a ball-earth system. For case 1, it might look something like this. So we have our ground. We've got the ball at its initial state, we'll call that state A. And it goes up to its peak at state B. And our system includes the Earth, which is that bottom line. For case 2, it's a little bit simpler, it seems. The ball just goes straight up from point A to point B. Now, since the problem doesn't say anything about the drag force of the air on the motion of the ball, we're going to assume that the drag force is irrelevant, it's negligible. Drag force is small, we could say, close to 0. Now for part A, now that we have our system, we can start to tackle the question. Part A asks to find the maximum height. Which is the height at point B for each case. So let's think about what the change in energy of the system is. Well, we know that the change in energy of a system is equivalent to the summing the change of the kinetic energy, potential energy, and the internal energy. And we know that's equal to 0 because it's an isolated system. And since we know that the drag force is negligible, that means there's no non-conservative or dissipative forces acting within our system. What that means is the internal energy change is 0. Now considering the kinetic energy and potential energy from A to B, change in kinetic energy is equal to 1/2 times mass times the velocity of A squared. That's the definition of kinetic energy at the point A. We subtract. Well, I suppose I should consider it from final to initial. So let's change the first term to this kinetic energy at point B, and the second term to the kinetic energy at point A. Similarly, for potential energy, the definition of potential energy is the weight times the height. And we're interested in the change from state B to state A. So we plug these back into our change in energy equation. We have our change in kinetic energy. And our change in potential energy. Now you can see that we can cancel out this common mass term. We also should understand that our datum, hinted at by the problem, let y equal 0 at the cannon. So y in this case we call HA in either case. So HA is equal to 0. So if we rewrite this, looks something like this. And if we solve for HB, our maximum height, symbolically, HB and it's nice to solve equations like this symbolically in physics problems, because a lot of terms will end up canceling out and you won't have to follow around what numbers you plugged in. So now that we have a general formula for our height, let's consider each case, because the velocities vary a bit from case to case, at point B at least. So for case 1, draw a little bit more detailed of a picture. So here's point A, and we have our velocity vector, 37 degrees from the horizontal. And it goes up till it reaches its max height here. And at this point, this is point B, its velocity at point B is completely horizontal. Now there's no change in the horizontal velocity at all. That is, it's not accelerating horizontally. The horizontal speed is constant. So VB is equal to the x component of VA. And the x component of VA is equal to the magnitude of the velocity times the cosine of the angle. And VA is simply 1,000 meters per second. Now we have everything we need to solve for our height. So if we plug in our values, and for G we'll use 9.81 meters per second squared. So for our units we've got meters squared per second squared divided by meters per second squared. This is going to give us meters, which is correct. So our height, point B, is going to be equal to about 18,459 meters, or you could say it's about equal to 18.5 kilometers. Wow. We really shot that thing up in the air, 18.5 kilometers. Which makes a bit of sense considering we're launching this thing at 1,000 meters per second. And it's only slowing down due to gravity. Now what about case 2? We need to find the maximum height for case 2. So we can copy our formula here. In this case, the ball goes straight up to its peak height. But the difference between case 2 and case 1 is that in case 2, when it reaches point B, there is no velocity at all at point B. Velocity at point B is equal to 0. So it simplifies our height equation a bit. So we could say that this is equal to, if we move the 2 down to the denominator, we could say that this is equal to VA squared divided by 2G. Or our units here are, again, meters squared per second squared divided by meters per second squared, which is meters, which is what we want for a height. And after we plug this into a calculator, we get a height of about 50,968 meters, or about 968 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 met 51 kilometers. Wow, also very big number. Now, moving on to part B of this question, which asks us to find the total mechanical energy of the system. Now, because this is an isolated system, there's no energy transfer between the system and its surroundings. So the mechanical energy is going to be conserved if there are no internal dissipative forces, like in our case. So what does that mean? It means that our change in energy is equal to 0, right? Or in other words, our initial energy at state A is equal to our final energy at state B. That doesn't change, and we can just call that E, which we know in our case is just the sum of the kinetic energy and the potential energy. And that particular sum is the mechanical energy. This is the same at any state in the isolated system. So the mechanical energy at state A, do some parentheses there, is equal to the mechanical energy at state B. That means there's two ways to find the total mechanical energy for this problem. Evaluating the mechanical energy at state A is a little bit simpler, because when you work it out, you might think, well, this looks exactly like it would at state B, except there's actually no potential energy at state B when the ball is at the initial point. If you'll recall, we determined that HA, our reference point, was 0. So our mechanical energy is equal to 1/2 times 20 kilograms times 1,000 meters per second squared. And if we plug that into our calculator, if we need to, which we really don't, we can look at this for a second and see that this is 10 kilograms times 1,000 squared, or 10 kilograms times 1 million, or 10 to the 7. Now, what about the units for this? Well, we've got kilogram times meter squared per second squared. That's the same thing as saying kilogram meter per second squared times meter. And this first term here is a Newton. So collectively we have a Newton meter or a joule. So that's the total mechanical energy in this system. I called it the mechanical energy at state A at the start of this line. But we know that the mechanical energy is conserved, and it's the same at any state. If we wanted to calculate this at a different state, say state B, this is also equal to the mechanical energy of the system. It'll look a little bit different though in the formula. Here we have more terms to calculate. So this would look a little bit different for each case, but they would ultimately be the same. 10 to the 7 joules. All right, that's it for this problem. Thanks for watching. If you have any comments, questions, leave them